Now, one of the direct mathematical consequences of Hooke's law of elasticity, which you'll see here, and I'll highlight it in green, is this actually creates what's known as a differential equation, because our force is related to acceleration, and acceleration is related to displacement. Now, differential equations are equations that you can solve. We won't be solving them here, but you can do it. But one thing about solving this type of equation, especially if you put force is equal to mass times acceleration in for the force, is that you get a proper solution to it that involves a trigonometric function. So interestingly enough, if you were examining these types of systems, there are a number of different ways that you can solve this. You can use sine, you can use cosine, you can use complex numbers and exponentials. But generally speaking, you get a system that looks like this. This is known as an oscillation. Right? So that's your standard sine looking curve. An oscillation just means that we go from positive, and then we get pulled back down into negative, and we cycle back and forth. Where this starts and stops can be changed, it can be moved around, all sorts of things can happen to it, but the general idea is you get this harmonic style motion. Right? That's the H in SHO. The reason it's called simple is there are some other things that we're going to introduce further on, such as damping, that can change the shape of this, but you get an oscillation that's back and forth. This is the same oscillation we talked about previously, because as we displace ourselves from equilibrium, there is a force trying to pull us back down towards it. So this is literally just an extension of elasticity. Now there's a number of different parameters that you can use to describe this oscillation, such as the period, the time it takes to repeat itself, as well as mathematical quantities, such as the angular frequency or the natural frequency. There's a whole bunch of them for you to choose from. The idea is we're dealing with something that's moving up and down, and eventually this motion will repeat itself infinitely. Right? So it'll keep going up and then down and then up again. Now, you can see this in every single system that we talked about, whether they're physical or not, that deal with oscillations. So if you take a pendulum, which is just a mass hanging by a spring or by a string, and you swing it back and forth, you'll see it oscillate. If you take a slinky and you let it hang vertically and move your hand up and down, you'll see it move back and forth. These are all described by this system. This holds true again for our non-physical examples as well. If you take a look at this climate style graph here, which I just randomly pulled out of the internet, what you'll notice is for each of the years, we have this same seasonal oscillation in the carbon dioxide concentrations. Right. So again, this type of oscillation comes directly from this idea that we're going to have forces that try to restore us to some equilibrium. And it will naturally give us the shape that you see whenever you have a system that is oscillating or moving around an equilibrium point and wants to return to that equilibrium point. Now, doing so is mostly, or figuring out the wave-like parameters is mostly a process of just working through the mathematics, and that's what you'll find for the other examples in this section.